Okay, so you have your monocrystalline, polycrystalline, both silicon. Polycrystalline gets about 18% efficiency. It's also a lot cheaper. These are polycrystalline. You can usually tell polycrystalline because they're usually like a dark blue color. They're also, you'll see them in a lot of like older electronics and stuff. And then there's monocrystalline, which is sort of using more like pure silicon. And that's what that solar panel is over there. That's why it's a little bit darker.
Polys are what you'd see more in like a clock calculator or something like that.
Yeah, you probably see them that. And I just say that because it's probably a smaller solar cell, so they can probably afford the more expensive.
You might find one.
I mean the poly ones is what you'd see in like a 20-year-old calculator or something like that.
Could be.
That's all.
Yeah, I really don't know.
It's got to give the middle
The
finger.
garden lights, those, solar garden lights, probably the cheap stuff.
What is it?
The solar garden lights, where they have, that small 1-inch square solar panel on top,
Yeah.
and, they don't last 2 months.
One way of really telling is if it's blue like this, or I don't know if you can see right here, but it basically looks like there's little shards of like triangles and things, then it's probably polysilicon.
Okay.
But then there's not really a whole lot of difference between the two. They basically get about the same efficiency, 18 to 20%. The only real difference is monocrystalline usually costs more because it has to be more pure silicon. And then beyond that, you have your concentrated photovoltaics. And this is the sort of stuff that they actually have on the space station because they need a very concentrated amount.
Right.
This isn't, you won't see this very often for terrestrial use. So up there, you'll see a solar cell like that, which is really strange. And then on top of that, you have a glass box like this, where you have basically a very, these lenses are actually about half the size of the box. And they concentrate the light down so much that, instead of getting 20% efficiency, you're getting about 40% efficiency.
So the power out per weight, volume, and size of the panel is a lot more.
Well,
Why don't they all do this?
what?
Because it's so expensive.
They're really expensive to make.
Because that deal with a lot of waste heat. Because that Fresnel lens, the one in hand, we could, probably melt a hole through, a chunk of aluminum and be full of sun.
Yeah.
If you get one of the big ones, the big screen TVs, we could melt through a railroad spike.
Something to do on a boring day.
Yeah, seriously, what are they on?
Skip the Fresnel lens with one framework and one of those completely clear shower curtains filled with water so it creates its own lens and then start sticking things underneath to put it.
We're doing cooking with science.
So there's a couple things that go along with this. Now, they are a lot more efficiency, or they are a lot more efficient. You get about 40% efficiency, but then you can also concentrate them a lot more because you have a smaller cell. So instead of having a 6-inch by 6-inch cell, you have something that's, maybe 2 inches by 2 inches. And then you might have a lens that will be 4 inches by 4 inches on top of that. So the lens is usually a little bit larger than your cell.
The efficiency goes up the higher, the brighter the light beam to the cell.
Yeah. So I mean, you can basically pack more of these into a smaller space. So instead of having like a huge array that you need to power your space station, you can just have, a couple, 2-3 big panels, and then you can power your whole space station or something.
Is there any good reason you couldn't use a portion of that power to run a few CPU fans and keep one of those things cool?
Oh yeah, you can do that.
Yeah, well, but then you lose you would waste that energy cooling it.
Yeah,
But wouldn't you still make more energy in the long run?
it depends on how much cooling you do.
You burn more than your extra efficiency from using that versus just.
There's a lot of people crunching these numbers, they're running these tests, trying to make this less efficient. Or more, excuse me, more efficient, yeah, excuse me. And
Well, if your problem is, say, space, and you want a more compact unit,
then yes, that can be a good one, but it's also gonna raise price a lot.
So, getting back to your flexible technologies, you got your SIGs, which is your flat copper, the different chemicals, and then you have your amorphous silicon. Both of these get about 10% efficiency. They're not really efficient. But the one advantage you do have with these is if you have a very specific application, say for like integrating solar cells for an iPhone or putting them onto a UAV or like a blimp or something, you can do that. These are very flexible, they're very durable, they can take a lot of stress.
You wouldn't cover a car with them, it wouldn't matter that above it, if you put a regular cell on the front of the car, but it would crash.
Yeah,
It's like a lot more easy.
How's the heat tolerance? Because I know heat tolerance is a big thing for solar cells, like we discussed in the pump cells. Are they better or worse than these standard silicons?
well, okay, the biggest concern with heat and temperature is basically if the solar cell heats up too much,
It's
then,
inefficient. I don't understand that.
well, not entirely. Sometimes you can dope a solar cell, like we talked about phosphorus and boron. Now, if you dope it with gallium, gallium actually allows a better flow of electricity. Gallium is also, it melts at like room temperature.
Yeah, they don't help me.
Yeah. So those are the chemical properties of that. And basically, if you can dope whatever it is you're using with gallium, then it can actually increase a little bit, very, very tiny amount, maybe the voltage or amperage that's going through your solar cell. And that doesn't sound like a whole lot, but like if you do that small change to one solar cell, after a huge array, or maybe, a couple 100,000 panels that all have,
2% more.
Yeah.
2% more, and there's 40 or so of these solar cells per panel.
It really adds up.
Yeah, it does. So, and they also call amorphous thin film. You'll see that too. I think the other chemical name for it is CDTE.
Yeah, which is thin film.
Huh?
I've heard of it before, there's thin film.
Yeah. But thin film, CDTE is like, that's like cadmium, technetium or something, like some weird, strange chemical blend. And then I think one of the most interesting things that's popped up in the last year or so, as far as a case study, has been Germany. Germany is a northern European country. So right here is Berlin. This is Germany right here. And they have a lot of cloud cover. And yet they're able to generate about 40% of their electrical needs from solar panels. And yet this is the average annual sum. I think this is kilowatt hours per meter squared. So, the equator is down here. Most of the heat is going to be in this band around here. So the real people that should be using photovoltaics would be, grid, Africa,
Southern England.
over here, Middle East.
Ecuador, folks.
Yeah.
What is it?
Yeah.
Ecuador people.
Yeah, exactly. Florida, and yet Germany's all the way up here, and yet they're able to generate 40% of their own electricity just from photovoltaics. And this is with cloudy weather, you know, mountains that are blocking the sun.
So we need to invade Germany,
Yeah.
steal their solar panels.
Exactly.
And set them all up
We'll
in the
get half
Sahara.
of our power from it.
Steal the solar panels, set them up in the Sahara where nowhere ever goes, so no one will ever find them.
And the
One
ones,
say it, no one will ever see it.
Oh.
In fact, that's mostly silicone, so you can just kind of sprinkle some,
kilowatt hour per meter square. Then we're figuring it, what's standard solar panels at the 20%, we're looking at 0.2 kilowatt hour, 0.2 kilowatt hours per solar panel.
0.2.
A meter of
I mean,
exposed area makes a lot of power.
yeah, okay, that's,
If
okay.
that's measuring the sunlight per meter square, and it's running at approximately 20% energy efficiency. And we're looking at 20% of the 1100.
1100 kilowatts.
200 kilowatts per meter.
Yeah,
this is over
That's a lot.
200 kilowatts per hour per watt.
Your house probably uses,
You reduce it by 2 million orders of magnitude.
the kilowatt hour math is very challenging.
We put solar panels on the roof of our condo. We make enough
Enough
to pay for the solar panels before the condo association got wise and made us take them down.
No, you need, about a 15 yield.
there's, that's the big thing is.
It's a 10, 15 year payoff.
Return on investment time.
Yeah, it's getting lower though. Instead of like 15 years, it's getting close to like 10 years.
It depends on how you set up your system too.
Yeah.
How efficient your system is, and you know, you should, how the weather is each year.
But if you go back to that one graph, like I was showing you guys before,
Have any questions again?
I'm gonna
Yeah.
put them there, I can do whatever I want.
You need a backwards button.
yeah, I do. Now, the one thing that I'm going to explain about this,
Completely ruined my house.
if you look at the way that all this technology has been trending,